Yeah, so hi, I'm Wenhao. I'm a PhD student here, and I'm going to present model effect types. So it is talk about model types. I gotta went to Steven's talk, and about effect. Gotta went to Megan's talk. So anyway, we want to design a better type system for effect handlers. So first, let's have a recap of traditional effect types. So what are effects? Megan has already introduced them. I don't want to. So here is a simple function int, which takes x an integer and increment it by 1. And another higher order function f takes the function f from int to int, an integer x, and applies f to x. Uh, we can apply f to int and 42, which gives us 43. This is standard. So these are all pure functions. And with traditional effect types, they are all annotated with an empty brace to mean that these functions use no effects. Yeah, so it means empty effect. So if we change the definition of ink to call an effect ask, uh, so ask is an operation that takes a unit and returns int, which we ask from the environment. We need to change the effect type of ink to the phrase ask to capture the fact that it uses the ask operation. And also, in order to apply the add function to ink, we have to change the effect annotation of each function arrow in the type of app to have ask, so that we can apply app to ink because we have to make sure that the app takes the argument, but it can use the ask operation. And in general, in order to allow applying app to any effectful function, we have to use effect polymorphism. So we have this for all E, where E is a type variable with abstracts over effects. And for every function arrow in app, we have to annotate it with this effect variable E. And similarly for ink, if we want to use ink in an environment with not only ask but also other effects, we also need to quantify over the other possible effects with an effect variable E here. And here is a handler for ask, which is a function that takes an argument from int to unit that use ask and some other effects. It handles the ask operation of this argument, so the whole function only uses other effects E. And again, we need to use effect polymorphism here. We have this for all E in order to allow this handler to be used with other effects. So as we can see, these are the type signatures for a function that uses ask, for a higher order function, and for handler for ask. We have to have this for all E and the effect variables E almost everywhere. They are very verbose, they are very annoying. And in particular, if we have an existing language and we want to add effect types to that language, we have to write every type signature in existing libraries to have this for all E and effect variables. So can we get rid of them? And our proposal is model effect types. So first, let's take a closer look at the definition of app. The definition is very simple. It just takes f and x, it applies f to x, but it has a very long type signature. And this is unfair because the definition of f does not use any effects at all. So uh, if the definition does not use any effects, why do we have to track this effect variables E in its type? So why don't we just track the effect, just track the fact that the app function itself does not use any effects? But this is impossible because with a traditional effect system, we have to annotate every function arrow with the effects that it uses. So there's no choice for us to not having these braces alongside each function arrow. So our main idea is to decouple effect types from function arrows. The most important concept is in the effect context. It is something tracked by the judgment. It tells us what effects can be used by the whole function. So, so now with model effect types, I've just had this simple type signature, and this at E is tracked by typing judgment. It's the ambient effect context F. It might be some arbitrary big E here. And this ambient effect context propagates through every type constructor. So for the argument function and for the result function of F, their effect contexts are both big E. In order to have some effect information in types, we use this absolute modality, which is square bracket with some effects F. So for F, because it is a pure function, we just need to add this empty square bracket to the whole type signature of F to track the information that F itself is pure. So suppose the amp in the effect context for the whole definition is some E. This modality overrides E to empty. So we know that for the function inside this modality, its effect context is empty, which means it is a pure function. Yes. And also by sub-effecting, we can still apply E any other effect context because if we have some function pure, we can of course apply it in any context. So similarly for ink, we don't need this for E and effect variables E. Instead, we use this square bracket ask to track that ink is a function that only use the ask operation. Yes. And again, by sub-effecting, we can apply ink in any context that with effects ask and possibly some other effects. So for handlers, we also have the relative modality, which specifies an extension to the ambient context. So here is the previous type signature for the handler ends. And with model effect types, we only need to wrap the argument function with this angle bracket ask, which means that this argument is a function that might perform ask, but this is a handler for ask. It handles the ask operation. So for the whole function, we do not necessarily need ask. So again, supposing the ambient context is some effects E, this angle bracket ask extends E with ask. So for the argument function, its effect context is ask and E. Yeah, which tracks the information that it might invoke ask. But for the whole function, it is still E. Yes. Yeah, and also, so if you remember the definition of ans, it is a pure function. So we can also add this empty square bracket to track the information that ans itself is a pure. Yeah. Yeah, so this is the type signatures we get with model effect types. We get rid of these these quantifiers and the effect variables. And we can do a bit more. We can assume that so these are all global functions. We can assume that global functions must be pure. So their definitions are implicitly wrapped with an empty square bracket. And further simplify the type signature. So in particular, you can see that for the higher order function f, it is a pure function, and we do not need to change. We do not need to change anything in its type. Yeah, and we can compose them together to see. Oh, pretty standard. And now I think I can show a bit more examples to give you a flavor of how it works in practice. This example of cooperative concurrency. We have two operations, this fork operation and this suspend operation, and we implement processes using an algebraic data type and some auxiliary functions and another for these operations. You don't need to understand the code. But I just want to show that with traditional effect types, you have these quantifiers, these effect variables, not only in functions, but also in data type definitions. We also have to be parameterized over some effect variables. Yeah, but with model effect types, we get rid of all of them. So the definition of the data type is very simple. It is exactly the same as what we have in a language without effect systems. And for these functions, we do not need effect variables. Instead, we just use some modalities to track the information that either they are pure functions or it is a pure handler that handles the group operation. Yeah, and here is another example. Suppose we have a list of functions f1 to fn. So f1 calls f2, f2 calls f3, and fn uses the ask operation. So with a traditional effect system, we have to allocate each function arrow with the ask operation. Yeah, because we have no choice, we must allocate each function arrow with the effects. And if we change the effect used by fn from ask to get, we need to change the effect in all these type signatures. So with model effect types, we do have a choice. Either we can wrap every function definition with an absolute modality, so that every function has a square bracket ask, and when we change it to get, we need to change all these square bracket ask to square bracket get. But if the global context provides some way to handle the ask and get operation, then we do not need to allocate anything in the function in the type signature of these functions at all. Because effects are decoupled from function arrows. And yeah, so we almost have exactly what we have before with other effect systems. Like they're just functions from int to int. Yeah, and I have some slides to introduce the correctness, but I'm not sure if I want to show them. But okay, so just give you some quick flavor of how the type system works. Maybe you're not interested. So we introduce the modality, we have this modal syntax, but so all these are in the correctness. They are inferred in the service language. But we have the modal syntax in the correctness, which introduces a modality for the type and a log in the context. Yes, and this modality overrides the embedding effects E to some effects ask as specified here. In order to use a variable, we have to make sure that this variable can be used after this log by checking this transformation operation, by checking this transformation judgment. And in order to eliminate the modality, we use that modal syntax, and suppose V is something with this modality, with this empty absolute modality. We use that mode to eliminate it, so we have a function binding with this allocation. Yes. Okay, we have more things in the paper. We have two papers on the same topic. The first one introduces the whole idea with the co-hackers, with some more extensions, and with standard type summoners and effectivity, and with a simple direction typing algorithm to infer these modalities. And we have another paper to study the relative expressiveness of modal effect types with some other effect systems. So we have a general framework based on modal effect types to encode other effect systems, and we have encoded various traditional effect systems in the literature. Yeah, and we have an artifact. So there is a toy implementation of the whole idea. So there are some ongoing work. We are trying to do better type inference from model types. We want to compare it to just capture tracking in Scala and some theoretical stuff. Yeah, so my takeaway is don't track effects on very function arrow. Instead, we should track them with modalities whenever we need to track them. So by doing so, we can get rid of all these modifiers and effect variables and have very succinct type signatures for these functions. Thank you.
Question?
So is there any example to show how to reduce some code or how to make the code simple, maybe in some application? So currently, maybe we mainly say about the principle, some things about how to using the Modal Effect Type. So is there any potential application or something we can use it?
Mm. Oh, I think it is something relevant to type system. So I don't think it really has any influence on the code structure. And yeah, but I think, for example, in Cangjie, every global, so maybe most function definitions have their type signatures alongside. And if we try to add an effect system to that, then we have to rewrite all these type signatures in existing code. Modal effect types, I think most of the type signatures just keep unchanged. And we only need to add very few definitions to, for example, those functions that represent the handlers in this language, or those functions that use some particular effects that are not provided by the context. So we have to annotate them in order to guarantee effect safety, to guarantee that we do not risk leaking any unhandled effects. So, yes.
Okay, thank you.
Last speaker of the day is Yixuan.
We generated it. We have to generate it.
Apologies. Okay.
LM is generating this one, so sorry, I have to wait. Okay, this is my presentation, LM enabled program synthesis. It is not about Cangjie, but I use some background knowledge about this in this presentation during my internship. So better to show up something. And it contains 3 papers. One is online prompt selection for program synthesis, and the second is guided enumerative program synthesis with large language.
Sure.
And the last one is guided tensor lifting. It is a more field application thing. I cannot click. Okay, what is program synthesis? Program synthesis is a technique that automatically generating code that satisfies the user's specification. And in program synthesis, that is a terminology called SYGUS, syntax-guided synthesis. And SYGUS requires the user to supplement the logical specification provided to the synthesizer with a grammar that constrains the space of allowed implementations. And this is a grammar. This is a very simple example of SYGUS. And the blue box is the context-free grammar. And the output of this specification can be a program like this. And the original synthesizer enumerates through the grammar without learned heuristics. So the search space is huge. And it is slow and not scale. If we provide heuristics, it will be better. And there is a popular algorithm for formal synthesis. It is called counterexample guided inductive synthesis. Like if we have a synthesizer, and synthesizer will give us something like this X, and the verifier will verify it against that specification. It says no, because when we have X equals to 1 and Y equals to 2, that is not true. So next step, we will add that to our counterexamples, the background knowledge. And synthesizer will give us another code like Y. It satisfies this counterexample. And verifier will verify it against the specification. It says no, because when X equals 2, Y equals 1, it is not true. So next time, it will be more complicated. And the synthesizer will give us something like this one. And the verifier will verify it against that specification again and says, yes, that's that. That is code. Checking against input-output specification is easy. Just execute the code like when the synthesizer synthesizes a code that satisfies those two counterexamples. That is really easy. We just execute the code. But checking against arbitrary formula is harder. Like the verifier, it needs to verify against that big thing. It is really hard. We need to use an SMT solver. So for formal programming synthesis, we have specified if your solutions are short and you are willing to provide some good heuristics. Now we have large language models. If you are willing, if you are writing in the popular language like Python or Java, and you don't mind a few mistakes, and also you can afford the compute. So there are 3 research questions. The first one is how to choose the best LLM and prompt. We can learn from the previous task. And the second is what if LLMs produce plausible looking yet fundamentally flawed solutions? Try again. And the third is how can we still use LLMs despite hallucinations? We treat LLMs as tools for ideas, not guarantees. That is our chance. Okay, this solution is in my thesis and it is under submitted. Okay, the first one is online prompt selection for program synthesis. Program synthesis users will frequently have not just one, but a series of synthesis problems to solve, like a function after a function. So there are multiple things. And large language models excel in program synthesis, but their effectiveness varies by task, LLM type, and prompt style. The user decide if an LLM is suitable, choose the best LLM, and determine the optimal way to prompt it. And incorrect choices lead to suboptimal results and higher costs, especially with commercial APIs. Like, for example, this is a standalone LLM. We have our input, and we prompt LLM. LLM will give us a candidate. We verify it. If it is wrong, we reprompt LLM. We ask it to give us another one until we find the correct solution. how to write the right prompt? Like, how do we prompt LLM? That is the thing. We can use multiple bandit algorithms to select the best LLM prompt combination based on reward from solving synthesis problems. And we use k-nearest neighbor as contextual multi-armed bandit. The term multi-armed bandit refers to a problem where an agent must decide between multiple choices, like from the 1 to k, without knowing the outcome. The challenge is determining the optimal arm to pull to maximize the total reward over a series of trials. And if we know the distribution of each task, like which task can be better with the prompt, like prompt A or prompt B or LM A, LM B, then we can try our best for the next task. So that is the multi-arm bandit controller. And we have two different models. The one is single multi-arm bandit. We have a query. We visualize it with our own visualizer. And we also have a predictor to predict which LM and which prompt we would like to choose, the pair. And then we allocate the cost, like how many tokens do we need to solve this problem. If it exceeds that token limit, we just say that the LM prompt pair cannot solve that one. And then we allocate the time we need LM to give us the solution, and then we deploy it. If we have the result, we will update the predictor with the reward, and the cost allocator with the cost, and the time allocator with the time. And there's also a multi-arm bandit. This is more like a human. First, we choose which language model we want, like ChatGPT or Llama or something else. Maybe a symbolic solver, this one. So if we choose an LLM like ChatGPT, then we can use the prompt predictor to choose a prompt for us and allocate the cost and the time and deploy it. And then we update everything. And this is a selection of our prompt styles. We have multiple prompt styles, and this is the result. The lower, the better. And the blue one is the virtual best. It means if we already know the results, this will be the best. And the orange one is our model, the single layer model. It is really close to the virtual best one. And the second topic is guiding innovative program synthesis with large language models. The standalone LLM, we can prompt and verify, but what if every prompt, every large language model, they all fail? What we do now? We have two different models again, frameworks, the PCFG instance and ILM instance. The PCFG instance is using the LLM as pre-trained syntactic guidance, and ILM instance, it is like iPhone, the integrated LLM. It uses the LLM as an integrated syntactic oracle. And for the standalone LLM, this is the prompt we use. And this is the prompt if the solution is incorrect. Okay, what if LLM is still wrong? Is the LLM close enough? Actually, it is. Though LLM guesses are wrong, the solution is still in the neighborhood of those guesses. And let's have some background knowledge. First, convert a set of LLM-generated programs into a grammar that captures the likely space of correct solutions. It is about the weighted grammar. And what is the weighted grammar? It calculates the number of times that each rule appears in the program. And what is a probabilistic grammar? The frequency of each rule appears in the weighted grammar. And the frequency of each rule indicates its likelihood of being cracked. This is PCFG framework. First, we have our input, that one. And then we prompt LLM. It will give us several candidates. We just prompt it. If it's failed, we reprompt it until several attempts. And then we can gather our failed solutions. Through the rule weights, we can extract the rule weights. And together with that grammar, input grammar, we can have a PCFG. So first, how to synthesize in the synthesizer, initialize expressions with the start symbol, repeatedly choose production rules to replace the leftmost non-terminal in the current expression. And the choices made by sampling from distribution over possible production rules. Repeat until depth limit is hit or complete program is found. If the depth limit hit, we complete the program. And if it is complete, we return for verification. This is a very simple grammar, this one, very simple one. And how do we enumerate from this grammar? We start from E. It can be extended to E plus E or T. According to the PCFG, we say that E plus E has a higher likelihood than T, so we choose E plus E, and so on, and so on, and so on, until we find a complete program, A plus A. We verified it is as no, so we go back again, and from T, A and B, A is a complete program, we verify it, and it is the program we want. And another search technique is called A-star search. It chooses paths based on minimizing path score. It focuses on paths with lower combined actual and predicted costs, and the score is the cost so far, plus estimate of the cost to complete the program. Still the same grammar, and it first initialize the queue with the start symbol. This is a queue to store partial program with scores. We have E. We pop it, and we expand it to T and E plus E. According to PCFG, we can say that the scores E plus E is higher than T. So the next step is we pop E plus E and expand it, update the queue. We pop it and expand it. And now we have A. We can verify it. It is way faster than the previous one. So A is a complete program. We find the candidate. And another framework is LLM Sense. LLM as an integrated. Sorry. LLM as an integrated syntactic Oracle framework, LLM Sense. There's a two-way communication. First, we send partial enumerative programs and a counterexample from previous iterations, and also the incorrect solution from previous iteration. And it returns updated PCFG with new production rules and updated distributions. Like we have input and the grammar. We can generate a partial program, like just a guidance. For example, if then else, nothing else. And there's a large language model. It will give us some helper functions or just complete that partial program. If we have that complete partial program, we can have, let's say we have a candidate, we can verify it. If it fails, we have a counterexample. Then we go back to LLM again with that counterexample and the partial program from the enumerator. Then the LLM will give us some new helper functions. Then we have the new solutions, some pile of solutions. We can update our PCFG. So next time, the search will give us a new partial program as well. So that is the loop. And this is the prompt we use for LLM Sense. And this is what LLM will give us. If LLM responds a complete program, we verify it. And if the LLM didn't give us a full candidate, enumeration keeps replacing non-terminals until none remain. And we also need to update the PCFG. It passes all helper functions add new helper functions as new production rules to any applicable non-terminals. For example, if we have a grammar like the left one, and we also have a weighted grammar, this is something in the middle of our steps. We already have the weights here. And LM says we can have program like x greater than 0 or x greater than y. So what we do now, we update our weighted grammar. And we also insert helper functions to the grammar. So next time, if the program requires a partial function using this one, so it can just choose this one. That is the one step, only need one step enumeration. That is faster. So by updating the PSFG, it dynamically updating the probabilistic distribution of a grammar rules allows the LLM to make mistakes, and it is cheaper prompts. The result, the A-star PSFG things, like it is the framework 1 with A-star search, it is the best. This is the state-of-the-art symbolic solver, CV5, and this is the standalone LLM, and it can only solve half of the benchmarks. So this one is definitely the best. Yes?
Are these also, all of the other ones are combined with LLM?
No, not this one. These two are combined with LLM.
Oh, right.
Yes.
Oh, it's not.
Yes. So LLMs can generate heuristics for SIGUS. Now we need to automatically generate heuristics for real problems. Can we apply the same techniques to generating other codes, like updating the old code? And I believe that is also what Huawei wants. And okay, let's go to our next topic is guiding tensor lifting. In program synthesis, previous all code works on all hardware. If the hardware got faster, your code got faster automatically. And hardware is now becoming more specialized with corresponding DSLs. And in program lifting, machine learning workloads are dominated by tensor code. Key to efficiency is the highly parallelized algebra. DSLs like Taco make this easy for new applications. Taco is the tensor algebra compiler. It is a fast and versatile compiler-based library for sparse linear and tensor algebra. Okay, we can write new code with new DSLs and new languages, but what about the lexicode? Do we need to, like, humanly, with our bare hand, to rewrite C to tackle PyTorch or NumPy or MLIR to JAX or C++ to highlight? That's painful for millions of lines of lexicode. What I want is just laying down, play with my phone, and the tool can do everything for me. And we are focusing on lifting C code to Taco code, but there's lots of other DSL that the work could apply to. This is a very simple input. This is a C program, and it is doing this one. So we can rewrite it into a Taco expression like this. AI equals to Bij times Cj. Taco expression can then be compiled to highly parallelized dense algebra. And Taco can speed up 1.8 times faster on the multi-core platform and 24 times faster on the GPU. This is the pipeline. We can split it into 4 parts. The LLM part is the stand LLM thing like we did before. And we also have 2 guidance parts and the search part, the enumerator, and also there's a verification part. This is the guidance part. If we have we have the solutions, the incorrect solutions, or maybe correct solution, it doesn't matter. We can generate the possible probabilistic grammar, and we can also use the dimensional analysis to get our left-hand side dimension. How to determine the left-hand side? AI. We look for main assignments. These are the main assignments, and it initializes to result. I don't think you really care about this, but let's say we can find the left-hand side by using this tool. Why do we use the analysis tool rather than LLM to give us left-hand side, because LLM is really bad at Taco. Taco is so low resource language. It can only give us like something A equals to B times J or something like that. It can never give us AI or AIJ. The index in the left-hand side is never accurate. So we need to write a tool to analyze that thing. And for the right-hand side, this one is the right-hand side. We can ask LM to do that for us. So this is it can be generated from learned heuristics from LM. If the response from LM is the top, so we can have grammar on the bottom with probabilistic as well, the weights probabilistic. And now we can search by using the weighted grammar. We also use A star enumeration. We choose passes based on minimizing pass score, and the score is the cost so far, and estimate cost to complete the program. And there are two different enumerators by using A star. The first one is top down. If we have a response like that one, we can have our top down grammar like that one, and expands from the root symbol downward like before, and it naturally handles nested or deep expressions. It estimates cost at node S by the minimal additional cost required to complete the partial program to a full expression. And there's also a bottom-up enumerator. This is a brand new thing. And the grammar here is for bottom-up. It builds expressions from smaller sub-expressions upwards. It finds short expressions quickly. And the estimate cost at node X is the difference between current length to predicted length. Also, they come from LM solutions. And the last part is the verification part. We have IO check. We check if the synthesized Taco expression can produce a program equivalent to the original C code based on input-output behavior. The process is like we generate random IO inputs and get the expected outputs. And we also need to instantiate Taco expression. We run Taco expression to concrete programs. We try all valid substitutions of tensor and constant symbols. Like for this one, this is the Taco expression. There's lots of valid substitutions, and we choose the correct one. And after that, we also have a bounded mode checking. It proves that two programs are equivalent up to a bound. First, we lower both programs to MLIR. The Taco expression, it is JAX plus NumPy to emit MLIR, and we can also compile them to C with assertions. We assert equality of outputs for all inputs up to a bound. And then we can use bounded model checking, CBMC and CBS5 to verify that assertion holds. These are the benchmarks. And we also have baselines. Taco is the previous state of the art, and TensorSpiler is also one of the state of the art before this paper, this work. And this is the result. The best one is a top-down enumerator. If we extend the timeout, it can solve everything. And this is the speed, synthesis speed. If we set Taco as the baseline, ours is 12 times faster. So double win. And the conclusion is it demonstrates that LLMs can be effectively integrated into program synthesis pipelines as heuristic engines rather than standalone solvers. And the success in lifting tensor kernels highlights that the potential of this approach for real-world software engineering tasks, including code transpilation, optimization, and DSL migration. And these are 3 papers of this talk. Thank you very much.